Hello and welcome back to Columbia University Physics Preceptor TV. Today we're going to be talking about experiment 2.6. It's the E over M experiment for the electron. This is a fairly straightforward experiment to explain. It's just a little tricky to execute. Let me go through kind of how it works. So the idea is to measure the charge to mass ratio of the electron. So we're not going to actually measure the charge, nor are we going to measure the mass of the electron. We're just going to measure the ratio. The idea behind it is that we have to somehow produce these electrons. And we use a filament to do that. So you have this nice picture in your book. I'm going to try to copy it as well as I can. There's a filament inside of this cylindrical plate here that carries a bunch of electrons on it. Now, what we're going to do is we're going to create a potential difference between the filament and this plate as such that we accelerate or pull these electrons off of the filament so that they accelerate out into the rest of our machinery over here. So now all of a sudden we have a bunch of electrons floating around here. Now, if the potential difference between these two is given by V, since the charge of the electron is E, the amount of energy it gains as it travels from the filament to the opening here is EV, the charge times the potential difference. Now, that energy is then going to end up being kinetic energy, so we have the equation EV is equal to 1/2 mv squared. That just follows from this part of the experiment. It has nothing to do with the rest of the stuff that you've read beforehand about the magnetic fields and stuff. But once it travels out here, we have an electron and that has a certain kinetic energy, and it's going to travel inside some magnetic field that we're going to create. I'll get back to later how exactly we're going to create this, but for now let's just suppose that there is a magnetic field that's pointing up here. Now, if there's an electron moving out, the right-hand rule, that's the force law, says that F is equal to the charge, which is E, times the velocity across the magnetic field. The right-hand rule tells us that if the electron is moving out of the page, the magnetic field is up, and it seems at first like the force is going to be to this side, to your left, but because the charge of the electron is negative, it's going to flip it, so there's actually going to be a force in this direction. Now that's going to then create a centripetal force that's going to make this electron travel in a circle. And if we in fact can measure the radius of the circle, we can tell a lot about the charge of the electron and also the mass. So the idea is that inside, this is going to be a big bulb here, and inside of here there's going to be a gas. And when the electron hits these atoms in the gas, it's going to ionize them. The electrons in those atoms are going to fly off. They're going to gain a bunch of energy. Then once these electrons recombine with the ions, it loses that energy, which is emitted as light. So instead of seeing the actual electrons, we're just going to see a bunch of light coming out. So it's going to look like a ray of light. So we can actually measure the radius of this. And since this is all inside of a bubble with gas in it, we're not going to be able to actually go there and measure the distance. So they've done it for us. They have a few pins over here that have a predefined distance associated with them. And you can find those in your lab manual, exactly what those distances are. So suppose that we then know the radius of this. This force, since it's a centripetal force, we know that EVB, which is the magnitude of the force, has to be mv squared over r. So we see that in this case we also have an equation just like over here that involves E over E and M. Also here we have an equation that involves E over E and M. We can in fact solve this equation for E over M, and if we can measure the magnetic field and the velocity and the radius, then we can determine E over M from either of these equations. The problem is that it's very difficult to measure the exact velocity of these electrons as they travel along the circle. So in fact, we're going to have to use both equations and eliminate the velocity by using both of them, and to find an equation for, we could technically find an equation for E over M in terms of the magnetic field and the radius and the potential, but instead we're actually going to find an equation for 1 over r. And you've been asked to derive this before you came to class today, so I hope that you've done that. The equation that you're supposed to have derived looks something like 1 of the radius is E over M divided by 2V times the magnetic field. Now, the equation that you derived is a little bit different. It has this extra term over here, and I'll get to that in just a second. But for now, just bear with me. This is pretty similar to the equation that you've derived already. Now, this magnetic field in here that I said just suppose that there is a magnetic field, well, it has to come from somewhere. And in fact, it has many different possible sources. The one that we're going to be concerned mostly with is the one that we're producing ourselves. So we have this Helmholtz coil. There's basically a coil on the top, and there's a coil on the bottom, and there's some current going through these coils, and as a result, there's going to be an it's going to be a magnetic field through the center of the coils. And there's a formula in the book, in the lab manual, that tells you exactly what the magnitude of this magnetic field is. I'll write it out here just to remind you. Now, in here, the only thing that we don't really know, or is that it's a variable, is really the current. We're given that the radius in this case is 33 centimeters, and the number of turns, n, per coil, is 72. So this ends up just basically being a constant times the current. And of course, we know what the fundamental constant mu naught is. So the only thing that's a variable in here, as I said, is just the current I. Now, this is one source. It's the main source of the magnetic field. But there are other sources of magnetic fields. Perhaps neighboring groups also have their machines turned on at the same time. So there are other magnetic fields due to that. The Earth has a magnetic field. So all these magnetic fields combine in totality into a total net external field that we can't control. The only thing that we can control is this magnetic field that we produce with a Helmholtz coil. And we do that by just changing the current. So in reality, this magnetic field that I've written over here should really be the sum of both the external field that we can't control and the field that we can control. Because the electron doesn't care about where the magnetic field came from, it just cares about what the total or net magnetic field is. So instead of B, we should really have something like the magnetic field that we control plus the external magnetic field and some magnitude or something of that. Now, in order to simplify our calculations in our experiment, we're going to try to align the one that we can control with whatever nature gives us already. So we're going to try to align or anti-align these. Because if we can have them to just simply be either parallel like this or anti-parallel, then this simply becomes Bi plus or minus, depending. Here you get a plus and here you get a minus. So Bi plus minus Be. So this should really be, once we've aligned them or anti-aligned them, this should really be Bi plus minus Be, depending on, as I said, if you align them or anti-align them. So how do we go ahead and do this? Well, we're going to have to measure basically the external field, and by knowing the direction of the external field, we're going to have to calibrate our machines to take that into consideration and be parallel to the external fields. And that's because we can't control what the external field looks like, so we have to take it the way it is. So inside your machines, it has two little compasses. It has one horizontal compass, and it has one that kind of looks like this. It's vertical. This first one is going to, once you turn off your machines, as long as they're all turned off, that you're not creating any magnetic field of your own, then this horizontal magnetic field, or a compass, is going to show the horizontal component of the magnetic field. So let's suppose it's pointing in this direction, something like this. Well, that then means that the magnetic field is along this diagonal. Now, we don't know exactly the vertical orientation of it, but what we can do is we can rotate our machine so that we can lift up the coil in such a way to align our magnetic field with the external magnetic field. Once we have it aligned in such a way, we can see that this thing starts rotating to determine the vertical component of the magnetic field so that we finally can lift our entire machine up. There's a little thing on the side where you can actually lift the coil up and screw it in place so that we, in fact, have our external, or our field aligned or anti-aligned with the external field. Now, once you have that, you can simply graph 1 over r versus the magnetic field that we create. And remember, the magnetic field that we create is simply simply follows from the Helmholtz formula. It's that constant times the current. And since we know what the constant is and we can measure what the current is, it says on the machine, we can determine what the magnetic field is that we're creating. And then we can simply graph 1 divided by r versus this magnetic field to determine what the slope and intercept is. And by doing that, we can determine what the ratio of E over M is, and also what the external field is. So that's pretty much all I have to say about this lab. Good luck and have fun.